Good morning. Welcome to Krishna's class. Today we look at the problem of resolving a vector in a Hilbert space into sum of two vectors, one in a given subspace or a closed subspace and to its orthogonal complement. Now, so the problem is this: H is a Hilbert space. M is a closed So the problem is this: resolve X as the sum of two vectors Y and Z such that Y belongs to M, Z is orthogonal to Y, and X is equal to. So this is the problem. How to solve this? Let us look at this problem in R book so that we get a feeling for it. So let us consider H to be equal to our model R. Now, if you take a given vector X, suppose this is a given vector X, and M to be the whole space, then so if X equal to Y plus 0, you know that Z is equal to zero. If M is a trivial subspace, namely, when these are all the extreme situations that we are looking at, then X equal to 0 plus X. So here I am sorry, X plus 0. Okay. Here X is equal to 0 plus X. Now 0 belongs to and X belongs to and X is orthogonal to 0. For that matter, any vector is orthogonal to 0. So this is the trivial situations that we come across. So we shall not bother much about it. So let us consider a non-trivial situation. So what should be, non-trivial situation in the sense that we consider M to be a subspace which is a proper subspace. So if then R2, it is a line passing through the oil. Okay. It's a line passing through the origin. It is a typical one-dimensional subspace of R. So this is what we have. This is R2. You have a subspace which is a line, and we are given a vector which we have to solve to a vector in M and a vector orthogonal to it. That's the problem. So the problem is finding this out. So how to proceed? Now you see, the problem is, so you have to write x to be equal to y plus z orthogonal to y. So how to get hold of this particular vectors? If you get one of them, you can get the other. Okay? So let us explore this problem. Now we consider a coset. This is x plus m. It's not a vector space. It's a line parallel to the given vector space M, and is usually designated by x plus m. So consider x plus m, which is equal to belonging to M. Now you know that, make an observation, but how to pick the whole thing? Let us look at the geometry of the problem. Now the problem is, we should get a vector which is orthogonal to this. Now you see, if I can get a vector which is orthogonal to M, okay, and such that it belongs to x plus m, and then this is x, this is something will be, let's call this z, and then you take the complement of that in M, that is going to be x minus. This is, we can draw the pictures and get a feeling. So you have the vector z, you have the vector x minus z, and their sum is going to be x. Now, the way in which we have constructed it in R2, they are orthogonal to one another. Okay? But now the problem is how to fix the point which will determine z. So the question is to write x to be z plus x minus, or rather x minus z plus z. So that z belongs to m and m and z. This is the problem. Okay. So write x equal to. So we want a determine the z such that z is orthogonal to x minus z, and their sum becomes x. So this is the problem that you have. Okay, this is the resolution that we are after, and call this y. Okay, we call set y. So this is the strategy. But how to get hold of z? First of all, we observe that z is in. So the way in which we have constructed, we take z in x plus cosec. Now you see that if you have a z prime, any z prime belonging to x plus m, or any x plus m, or any z prime belonging to x plus m, norm of z prime square z prime is greater than or equal to. So z should be a vector such that its norm is minimized. Okay, so this is what we want. So we want, so we having minimum now. So we recall the theorem that we have proved earlier. What is it? If x plus m is, so from what we have explored already, in the last lecture, such a z exists provided provided what are the conditions that you need. Z plus x plus m is closed as well as honest. So that is a condition. Provided and in fact there is a unique choice. Okay, and this choice unique so we have proved this theorem that if you have in a Hilbert space a closed convex subset, we don't need even, then there exists a unique vector whose norm takes the minimum value. Okay. So what we are searching for is such a position, and this exists. Okay. Now M is a closed space. Hence x plus m is closed. So also m is convex. Now it is immediately seen, it is easily seen that if x1 and x2 belonging to x plus m, then yeah, zt equal to that is the line segment joining x1 and x2. So that means you choose any 2 points and the line segment joining them belongs to x plus. This is quite easy to prove because you see that x1 is equal to z1 plus, so use z1 plus x, x2 equal to where belong to here. So compute this. So one would easily see that What is this? This is equal to this is equal to sorry. I'm sorry. And that's equal to x and 1 minus t z1 plus t z2 belongs to. Therefore, to see that for z1 plus z2, hence it is convex. Okay, hence it is convex. So you have x plus m closed as well as, I am not giving the proof of x plus m is closed. M is closed, therefore x plus m is closed. And that's very easy to. That is very easy to verify. If you take an xn that converges to x, sorry, if you take a yn that converges to y in m, then x plus yn converges to x plus y. Okay, that means x plus yn is a sequence in x plus m which converges to a vector. So therefore, you can argue this way: choose a vector. Okay, it's easy. Choose a sequence, a Cauchy sequence or a convergent sequence of vectors on x plus, say, call that Zn. So Zn converges to some Z. Each Zn belongs to x plus m. Therefore, each Zn is equal to x plus yn for some yn, because it is in x plus m. Now take the limit. Okay. Take the limit. See that y plus or what you call x plus yn converges to x plus y, where y belongs to m. Okay, yn converges to y belonging to m. Therefore, x plus yn converges to x plus y belonging to this x plus m. That's the proof. But that's easy. It's easily seen that. I'll just put a line here that the convexity is easily. Sorry, convexity we have verified. Closeness. follows closeness. So we have seen that X plus M is both closed and convex. Now apply the result that I was invoking earlier, and you would immediately see that there exists a minimum. So this is the crucial part of the this is how you work it out. But the important part is show that it's off. So let us now state the main theorem. Okay. So that is in R2. You can directly see in your diagram all these properties. So we shall prove it in the general context. So we'll make the statement of this. Let subspace of the Hilbert space then A has a unique decomposition X is equal to X sum of and M plus. That is one statement. The second statement is that Px are the nearest point to X This means that Z is the nearest point. This will be your empire. This is it. Okay? And y. Y is the nearest point from x to get a geometric insight. We will always work in R or R3. There you can draw pictures. Yeah. And in Hilbert, I'll draw the picture again. Be clear and make all these statements clear. The third point is that the mapping if the mappings P from Hilbert are fourth statement is that norm of this is Pythagoras theorem. This is Pythagoras theorem. Okay. So we have x resolved into sum of two vectors Px and Qx, Px belonging to M and Qx belonging to M. Further, norm of x square equal to norm of Px square plus norm of Qx square, and in fact you can show that Px belongs to M and Qx belongs to M pair, therefore they are mutually orthogonal, and you use that orthogonality to establish D. So D is a very simple consequence. Now let us prove this theorem. First we prove if such a decomposition exists, it is unique. Now this is the one that we want. Such a decomposition exists, it is unique. Okay, so let us do the following. That is this is what you want to. Suppose here we are giving. Suppose x equal to x prime plus y prime, and suppose x prime equal to 2x which is also equal to, I'll put it this way, y prime x, which is also equal to y double, sorry, z prime x and y double prime equal to px and z double prime equal to qx are two possible solutions. That is x is equal to y prime z prime and that is also equal to y double prime plus z. So this relation, that is x is equal to y prime plus z prime, which is also equal to y double prime plus z double prime, implies y minus y prime minus y double prime equal to z double prime minus z prime. Okay. Now we observe that y belongs to y prime belongs to M, y double prime implies y prime minus y double prime belongs to M. Okay. The second statement is this. Similarly, z double prime Hilbert, and Hilbert is a subspace which implies minus z prime belongs to, that is Hilbert is a subspace. Therefore, we have is equal to, which belongs to M. Okay. So y prime belongs to but only the zero vector. So the resolutions, if they exist, are unique. Thus, the decomposition X is unique. So we have proved the uniqueness. Okay. Now we prove the existence. Existence. Okay. So we do it as follows. Say, let us recall the picture that we have. This is your M, this is your X, and there is the coset X plus M. Now what we do is, we know that we identify Z belonging to such that norm Z is minimum for all elements, among all elements in X plus M. Now you have M is a closed convex closed subspace and hence convex. So we take the set as X plus M. There exists a unique. So define norm Z is less than or equal to norm of X plus any element. Norm of Z1 where for every X plus M belonging, for every Z1 belonging to X plus M. Okay, that is, it is the vector minimal norm in which exists. And if it exists, it is going to be unique, and that we have already. Now define Px equal to So that now Px, so we so what do we have? Now we claim for Qx belongs to expression, which implies Qx equal to x plus y for y for some y belonging, which implies what? Px equal to x minus x plus y is equal to minus y, and that belongs to M, that is y belongs to okay. So we have proved this. So P is a map, some map from H. We shall prove that both P and Q are linear. Okay, so that's we have. Now what we assert is that Qx belonging to now the next claim is or in other words that this is going to be so Qx is going to be so we have to show that Qx is orthogonal to M. So Qx is orthogonal to M, or Qx belongs to M prime. Let me prove this. So we choose some y belong to M. Equal to 1. Okay. So that we have such a element there. Now put qx. Now we have to show that the inner product of z with that's what we have to. Okay, so we prove it as follows. The inner product of z with z, this is equal to norm of z square. Now this you know that is less than or equal to norm of z minus alpha y whole square. What is alpha y? Alpha y is a scalar multiple of, see, alpha y for every alpha belonging to C belongs to M, because M is a subspace. Okay. Therefore, this is some other element of M. Okay. So this we show that this is equal to this is minimum now. So no other, see, this z minus alpha y is an element of say alpha y is an element of M. Therefore, this is z minus alpha y, and z minus alpha y is in M. Therefore, sorry. Let us work it out. Yeah. Okay, let me do that. So alpha y, say this is alpha, or some alpha. Need not be here, it can be here also. Okay. What is z minus alpha y? This is your z. This is z minus alpha y. Z minus alpha y is essentially this vector. It's the distance from z to alpha y. So it is this length. But this length is certainly greater than or equal to norm of z square. That's the argument. For any point here, it is alpha y. Therefore, this is z minus alpha y will be the distance from z to. So this is the distance from arbitrary element of M. Okay. And this distance is certainly greater than the distance from Z. Why it is so? You see, you are essentially taking an element over here, okay, in x plus M. Okay. This is the distance of Z to 0. So the distance from Z of Z to 0 is certainly less than or equal to the distance of Z to any other element of M. Okay. So this inequality flows. Now what is this? Let us work it out. Now this would turn out to be, and this is actually our okay. Now let us work this out. If you compute this, this is going to be ZZ minus alpha YZ minus alpha conjugate ZY plus alpha conjugate inner product of Y with Y. So this is equal to 1. This is equal to 1. Therefore, you get alpha conjugate. Now we make a specific choice of alpha. So this inequality is true for any choice of alpha. Therefore, that implies That implies 0 is less than or equal to cancels minus alpha conjugate alpha. This is what it is. Because now y equal to 1. Right? Now choose, make a choice of alpha. Alpha equal to conjugate. It's a complex number. Okay. Therefore, the above inequality becomes 0 is less than or equal to C mod whole square, and this is again mod z minus y whole square, and this is again mod z minus y whole square, and they cancel out, and this is equal to this. Okay, this is equal to minus whole square. So they cancel out. Therefore, we get 0 less than or equal to, but this is negative. 0 is less than or equal to this, and this is 2 only if that is this is true for every y. Okay? That is z belongs to so z belongs to thus we have the following results. Ex belongs to M and So this is the result that we have. So now we have to show the point. So you take y equal to. So we have to show that both. Where is our picture? Our picture is this. So we have x here. We have this is x plus m. This is z. This is y. Z is equal to x. Sorry, z equal to x. Y equal to x. Now we have for y belonging to m. This is true for any y. You have this is equal to Ex plus Qx now Px minus y belongs to M. And Qx belongs to M. Therefore, we get the following. And this relation I am writing for every y not the specific y that I have designated there, or I can, to be on the safer side, I will calculate this so that you have no confusion. For every y1 belongs here. Therefore, what you get? You get whole square equal to norm of whole square. This is because this belongs to M and this belongs to M. Therefore, by orthogonality, you get this result. Okay. Now you see that when is this minimized? The distance from x to see when we take so norm of x minus y1 is the distance from x to M. to y1 belonging to and when is this distance minimized? It's actually norm of qx square plus this one. So this is minimum when norm of px or y1 equal to okay, and which is equal to 1 according to our original notation. Okay. Therefore, at the minimum distance from x into n. So this is the minimum part. So this completes the proofs of so our claim was this, that px is at a minimum distance from x to m. So we take an arbitrary element y1 here and calculate this, and that is the calculation that we have performed. It's going to be the what is this norm of x minus y1 is going to be equal to norm of px, because x you can write as px plus qx. So it is norm of px. Oh yeah, we wrote this. So which is px plus qx minus y1 whole square, and that's by orthogonality. You see that px minus y1 is there and qx is there. Qx is in m per, px minus y1 is in m. Therefore, they are orthogonal to each other, and therefore you have this norm of x minus y1 whole square is equal to norm of px minus y1 whole square plus norm of qx whole square. And when is this minimum? Okay. Y1 turns out to be the point which gives minimal distance from x, provided this is minimum. When is this minimum? It's a sum of two positive terms, and this happens if you can make this 0. Okay, that is 0 only when px equal to y1. Okay. So y1 is equal to which implies px is at the minimum distance from x. This completes the proof. So we have got now qx is the minimum distance from x to m per, px is the minimum distance from x to, okay. Now we prove the following. What are the things to be? Therefore, Px and Qx are the nearest point to x in M and M per perspective. The mappings P from H to M and Q from H to M per are linear. That's important because it is not visible. The way in which we have chosen, we have not chosen imposed any condition on N. So let us compute this. Now the next statement is C, P and Q are linear. So to prove this, we do the following. So we have to show that P of alpha x1 plus P of alpha and Q of this is what we have to. Okay. So let us compute this. So we will calculate this. So P of minus alpha 1 Px1 plus alpha 2 minus x2. This let us compute. Now this is equal to, see, P and Q, there is a relation, so we write it in terms of Q. So what do you get? X2 minus same sort of argument. That means Px1 is equal, so this is equal to alpha 1 into x1 minus definition. This you simplify. So you get alpha 1 x1 and alpha 1 x1 cancels, alpha 2 x2 and alpha 2 x2 cancels. So this is what you get. This is equal to Q of this is equal to, let us work it out. So it is going to be alpha 1 alpha 2 qx2 minus q of so this is what you get. So we get the relation that P of alpha 1 x1 plus alpha 2 x2 minus alpha 1 px1 minus alpha 2 x2 is equal to alpha 1 qx1 plus alpha 2 qx2 minus q of alpha 1 x1 plus alpha 2 x2. Okay. Now you see that the left hand side belongs to M and right hand side Therefore, from the equality, both belong to which is equal to minus of next, and this belongs to, so both LHS and RHS belong to M and M per. Hence, the only common element of consists of only the zero elements. We have equal to 0, Q of that means both P and Q are it's wonderful. So these two are linear. Now we prove the last part, and that's very simple. The last statement is that so X is equal to by Pythagoras theorem. So that completes the proof of the theorem. Okay. So every vector in H is endowed with a unique mutually orthogonal resolution, okay, or decomposition. So we just sum up in one sentence. Yes. Oh, let's go here. This is the unique solution that we have. X belongs to. This is the theorem that we have. This is such a unique solution. Okay, it is in this context that we have used the minimal norm theorem that we have proved it. Okay, now we make a corollary, simple corollary. The statement is that if n is not equal to m not equal to h, there exists a y belonging to h, y not equal to 0 such that y belongs to m. So we prove this. And y equal to define y px, then px implies x does not belong to, sorry, x is not equal to px. This is the reason. Since m is not equal to x, there is a reason for that. Okay. Therefore, what do you get? Therefore, qx equal to x minus px, which is not equal to q. So this completes the theorem. Okay. So y is equal to, so you have this result, and from that you take y equal to x, you get the result. So I think that's the main theorem that we have today. It's an important result that you have in Hilbert spaces, that given a Hilbert space and a closed subspace of that, any vector can be decomposed into sum of two vectors uniquely, one belonging to M, the other one belonging to M. That is the so it's the orthogonality of these two spaces, M and M, which allows you to for solution. You see that you get a nice rectangle coming up. The R2 you have seen this. Okay. So you get a rectangle because of the orthogonality. So you get a parallelogram with all angles pi by 2. Therefore you get a nice rectangle. So thank you very much. In the next lecture we will try to explore the representations for linear functions on spaces. Conclude today's lecture. Thank you very much. Yeah, before I conclude, I want to make one more statement that these lectures are essentially directed to the postgraduate level students. Okay, right? Somebody asked that question. What is the audience to which you are lecturing? So this is essentially the postgraduate level students. So thank you very much.